Unit Operation Classroom. Today we are discussing inverse response characteristics in process control. My name is Shekhar Bhattacharjee. The problem is a process exhibits an inverse response to a step input. We'll see what is an inverse response. Then, if that is so, which of the following statements is or are necessarily true? So there can be multiple true or false. So this is a multiple select question, which is MSQ. That is, more than one options might be correct. So let us start this one. So first, let us see what is an inverse response. A process shows inverse response when, after a step input, the output first moves in one direction and then finally settles in the opposite direction. So let's see. We'll explain this in more details here. So for a positive input, if the final steady state is positive, the response initially goes negative. As we said, after a step input, the first moves in one direction and then finally settles in the opposite direction. Similarly, it's just opposite true. If the final steady state is negative, then the response initially goes positive. Okay. So here, as you can see, that in this case, the final steady state is positive. Say it goes to a value of 1, but initially it goes negative. Okay, so here this is a typical response curve of a inverse response where it initially goes negative and then it starts picking up and it finally goes to the steady state, which is in the positive. So that is basically inverse response. Okay, so we look at the more characteristics of the inverse response. Why inverse response happens? So inverse response happens is caused by zero in the right half plane. So here, zero in the right half plane called positive zero. So let's take a typical transfer function which shows inverse response, which is like this, where of course tau and tau 2 are the process constant and tau z is called zero time constant. Okay, so here to have to get the zero of this transfer function here, we can say this, put that equal to 0. So s would be equal to 1 over tau z. Since tau z is going to be always going to be greater than 0, so s is going to be greater than 0. So explain that is a condition for inverse response. Okay. So basically what it says, what is the option A? It says a transfer function has a positive 0. So as you can see, so this is 0 and these are the poles. So it has a positive 0. So option A is true. Okay. Since this is positive, so it has to be s is greater than 0, that is positive. Option B is just the opposite of this one. It's a transfer function is a negative 0, since the opposite of this one. So option B is false. Okay. All right. We'll discuss in detail the option C. Initial direction of the step response is opposite to the final steady state value. So we have seen the typical characteristics here, that we have seen that the initial direction was negative here and finally it settles in the positive. So let us take some typical values. Just for an example, let's take that k is equal to 1 and tau z is, let's say, is equal to 0.8. This is 4. This is 1.5. Okay, just as an example. So what is the 0? Say s would be equal to, of course, equal to 1.25, which is greater than 0. So this, of course, satisfies the first condition of inverse response, that is as a positive 0. Okay, that's in the right half plane. If we take this one and do the analytical solution, I'm not good for a step input. Of course, this is equal to ys over xs. Okay, is this one. So if xs is equal to 1 over s, which is for step input, so for the response, the ys is going to be like this. And if we take the standard solution, that's what the standard solution is. I'm not going into the details. So we have taken some typical values. If we substitute that, then that becomes a response for the initial value. Of course, at time t is equal to 0, this is going to be equal to e to the power 0, that would be equal to 1, and this would be also equal to 1. So this is equal to 1 minus 1.92 plus 0.92, so that's 0. So of course, as we say that this, of course, initially the value is 0. Okay, check the initial slope. That is in which direction the curve is going. Is the curve going in this direction or this direction? So we can check. So how do we do that? We take the derivative, find out the slope at the point 0. If we do that, so this is just simple calculus here, and we do that, and we get the derivative at 0 plus, which equal to negative of 0.133. So it has a negative slope like this. Okay, so of course, the initial value is 0, and it's going in the negative direction. Okay. Alternatively, of course, we can just see that for initial slope, finding out the initial slope of a transfer function, we can just use this equation here. The initial slope at t is equal to 0 plus would be equal to limit of s tending to infinity s square ys. So this is my s square here, which is this one, and this is for a step input we have seen before. So we just rationalize this one here. So how do you find out what the value of s tending to infinity? Let's do some quick assumption. Let's take the highest power. So this would be equal to s, for the numerator, it is going to be negative of 0.8 s squared. This one highest power, we are taking the highest power. And of course, for the lowest, for the denominator, the highest power would be equal to 6 of s squared. Right. So if we do that, so if we put this over this, so it will be negative of 0.8 divided by 6. So that's negative 0.133, which is the same value what we got here. So either way, you can find out the initial slope. And we see the initial slope is negative. So this slope is equal to negative of 0.133 going in the negative direction. So the response starts at 0 and then immediately moves downwards. Okay. Now we have to see the steady state value to confirm whether this is a inverse response characteristics. But now we find out the steady state value. So this is the one which we have seen by putting some typical values for the transfer function for the response of the curve. And of course, the steady state value, course, the steady state value, y infinity, of course, then if you put infinity, this is going to be equal to 0, this is going to be 0, so that's equal to 1. So as you can see, that the steady state value is going to be equal to 1. So it just goes like this, and then of course it will be like this. Alternatively, we can also use the final value theorem. We know basically for the final value theorem, limit of t tending to infinity of yt for a response curve would be equal to, we have to put s is equal to 0 for sys. Okay, these are all shown in this website here. So if you do the calculation, see that's equal to 1. So either way, you can show what the final response curve would be. So we have proved that. Let's go here. So we have proved that for this particular inverse response curve, so initial value is equal to 0, then it has a negative slope, and of course it has a final the value is positive. So that is a typical characteristics or the condition for inverse response, that the initial direction slope would be opposite to that of the final steady state value. So this was negative and this is positive. So this satisfies the characteristics of the inverse response. So let us quickly go here. So each option, we see that option A, its transfer function has a positive 0. We have seen that that is true. This is just the opposite of it. So this is option B is false. The initial direction of the step response is opposite to the final steady state value, which in our case, initial step direction was negative and this was positive. So this is also true. The system is unstable due to a 0 in the right half plane. We know that the stability does not depend on the nature of the, does not depend on the nature of the zeros. It depends on the poles, nature of poles. Condition for instability is that at least one pole in the right half plane, that is pole with at least a positive real part. Okay, so it depends upon the poles and not on the 0. So this is, of course, is false. So which one is true? A is true and C is true. So these are the two. So A and C, these are the correct options for this MSQ. This is false. Finally, let us look at the practical application of this problem. That means where we can expect inverse response. For an exothermic CSTR temperature response, what the typical industries like the polymerization reactor, where you use CSTRs, nitration reaction, halogenation reaction, or oxidation reaction. So these are typically exothermic reaction. Let's say the input variable is increase in the reactant feed flow rate. So whatever the CSTR is, the feed flow rate is increased. And let's say the response in our response is the CSTR temperature. Okay. So let's see what happens if we have an inverse response, or how we can have an inverse response in this case. If the feed temperature is lower than the CSTR operating temperature, that means if say this is the CSTR, if the feed temperature, this temperature is lower than the CSTR operating temperature, let's say steady state temperature, initially the temperature may drop due to cooling. But after some time, the exothermic reaction heat surpasses the initial cooling effect and eventually attains a steady state temperature. So initially there might be some kind of a cooling, so the temperature may drop, but later because of the exothermicity of the reaction, the temperature starts rising and finally it goes to a steady state, where of course the rate of heat generation would be equal to the rate of heat removal. Okay.